Okay, welcome to Calculus. Today we're going to finish up the material from the course, and the one topic we have left is section 8.3, Applications to Physics and Engineering. So we're using James Stewart, 8th edition, Early Transcendentals. And if you want to follow along in your book, section 8.3, about page 560. All right, so this chapter talks about hydrostatic pressure. So suppose you have some sort of flat plate that's underwater, and suppose that the area is A. Well, this would be the height of the water here. A formula from physics tells us that the water pressure is equal to P equals the density of water times G, which is 9.8 meters per second squared, times the depth D. So D would be this depth right here. So for water, we have rho is equal to 1,000 kilograms per cubic meter. So that's the density of water there. And G, 9.8 meters per second squared. Okay, so the water pressure is given by this formula right here, rho G D. Then one can ask the question, what is the hydrostatic force? What does the force do to the water on this plate? Like, if you were this plate, what force would you feel from the water pushing down on you? Well, it's basically the weight of the water above this plate. So if you calculate out the total amount of water above the plate, you just use the formula, force is equal to pressure, capital P. So this is a capital P here, and that's a lowercase p. Let me make it a little bit bigger so you can tell the difference better. So force is equal to pressure times area. And if you work it out, the area times the depth would be the volume, right? So the volume of the water above the area would be the area times the depth. It's just a big rectangle. And then if you want the weight from gravity on that, you would multiply the volume by the density to turn it into a mass in kilograms. And then you'd multiply by G to get the force due to gravity. And as you can see, rho GdA, same thing. So this is the formula you should remember. Force equals pressure times area. And pressure is density, gravity, times the depth. All pressure cares about is the depth, given gravity and the density are fixed. All right, so let's try out a simple problem, the simple aquarium problem. We'll calculate the hydrostatic force due to water pressure on the various sides. So let's write our formulas out. So pressure as a function of depth is rho G D, and force equals PA, force times pressure. Okay, so suppose we have an aquarium. And let's give it some dimensions. So let's say this is 2 by 3 by 4. And let's suppose it's full of water. So it's full with water. Okay, the exercise we're going to solve is to compute the force due to water pressure on the bottom. So part A. Find the hydrostatic force, I'll abbreviate it a little bit, on the base. The base is the 2 by 3 area there. And we only have to do one side. So how about the 2 by 4 side right here? And I duplicated this height of 4 over here. So part B, let's find the hydrostatic force, so I'll just abbreviate it, hydrostatic force on the front face, on the 2 by 4 face. Okay, part A is really easy. So we know the pressure at that depth. So the pressure at a depth of 4 is equal to the density, 1,000, times gravity. And we just leave it as G, times the depth, which is 4 meters. Oh, by the way, we have to be in meters in order for these to work out. So assume we're in meters, standard metric units. Okay, so that's the pressure. So to get the force at the base, so we're solving part A right here. So to get the force, we would multiply the pressure at 4 times the area of the bottom, 2 times 3. So simplifying, we get 6,000 times 4, 24,000 Gs. That's a pretty big force. 4 Gs is a lot for somebody. 24,000 is a huge amount. So that's the force on the bottom. Okay, so that did not require any calculus at all. What does require calculus is the face. So think about that for a minute. How would we compute the area, how would we compute the force on the face when the pressure changes as the depth changes? In other words, see, let's say you take this front window and make a little slice. So that little slice will have a thickness of dy, and the depth of the slice, let's call that y. It's now a function. It changes with y. So the idea is to recreate what we did here, but find a little force, dF, on this little slice of the front window. So using the force equals pressure times area, well, we need to find the pressure as a function of y times the area, dA, of the little slice. Alright, so let's work it out. So let's work on part B. Okay, so the area is 2 times dy. So dA is 2 times dy. The pressure as a function of y, well, y is set up to be exactly the depth. So the pressure as a function of y is equal to rho 1000 g y times y. So dF, the force due to the water that's pushing out into that little slice of the window, would be the multiplication of these two. So it looks like it's 2000 g dy. And then we simply sum up the force on all the little slices as y ranges from 0 down to 4. So we integrate all these forces. So it would be the integral from 0 to 4 of 2000. I forgot the y here. Sorry about that. So this y would go right there, say. So don't forget that y. So 2000 g y dy. Let me fix this. So 2000 g y dy. Alright, so that's dF as a function of y. And finally, we just have to integrate that. So you would take out the 2000 g, integrate the y, so that's y squared over 2, evaluate it from 0 to 4. 16 over 2 is 8, so 100, so it looks like it comes out to be 16,000 Gs. And what's a little odd sometimes is the force on a front window could be greater than the net force on the bottom. So it's a little strange, but it definitely can happen if the area is big enough. Alright, so this is our basic example of how to compute the net force due to hydrostatic pressure. Why don't we try one more with a triangular region. Alright, so let's say we have our water level like this, and then below it we have a window, a triangular plate like this, and suppose this is 2 meters by 4 meters. Suppose the tip of the triangle is 3 meters below the depth, below the water level, the surface of the water. Find the hydrostatic force on one side of the triangle. So I'll just abbreviate it. Find the force on one side. If you say both sides, they actually cancel out as vectors. So on one side. Okay. So you might want to pause the video for a minute and see if you can solve this one on your own. It is a bit more challenging. Alright, so let's see. Let's draw a slice. And let's let y be the distance to the top of the triangle. The length of this rectangle changes as y changes, so why don't we call that x. the thickness of this little slice is dy, because that's y. Okay, so first we need dA. Well, it's x dy. Trouble is, x and y are different variables, so we need to use similar triangles. So you see, x over y must equal 4 over 2. We're looking at this triangle and the big triangle. So the little triangle is x to y, the big triangle is 4 to 2. So 4 goes first and then the 2 over there. Alright, so solving for x is equal to 2 times y. So this implies x equals 2y. Okay, so we have dA. So dA is equal to 2y dy. Next, we need the pressure here. If y is the coordinate of this slice, its depth would be y plus 3. So using the depth formula, the pressure as a function of y is not the depth here. It's related to the depth. So it's equal to 3 plus y for d, so 3 plus y, that's the depth, multiplied by g, multiplied by 1,000 for the density. Okay, so now we have the pressure and the area, and we can integrate them to get the force. So dF would be the product of these two, so it would be P of y dA. So putting everything together in an integral, so the force would be, well, y ranges from 0 to 2. So the integral from 0 to 2 of 3 plus y g 1,000 times 2y dy. And I'll leave it as an exercise for you to work out this integral. You would simply need to distribute the 3 plus y, factor out the constants, and then integrate term by term. It's not at all difficult. Alright, so this is part 1, the end of part 1. This is how you find the force due to hydrostatic pressure. And next we'll look at the center of mass, the centroid. How do you find the center of an object? Like the center of a circle is right in its center, right in its middle. You could find the center of a square or rectangle without too much trouble. But how do you find the center of a triangle? So the derivation is a little bit involved. So for this video I'm going to skip the derivation and just give you the formulas. And I'll provide some information later on how it's derived. So here's the setup. So we have a figure, and the figure is what's called a two-dimensional lamina. Think of the graph underneath a function. So we have the graph of a function. Y is equal to f of x. So some examples. Well, we could have and we'll do this example, we can have a triangle. So y equals f of x. So suppose this is the base b and this is the height h. We could figure out the formula for this, right? The slope would be, it's a negative slope, and the change in y is h, negative h over b. And the formula would be f of x equals negative h over b, x plus the y-intercept is h. And you can check. When x is 0, y is h. When x is b, y is 0. Alright, so we'll keep this for later, and we'll find the centroid of a triangle. Okay, so we have in general, we have a graph of a function from a to b. Now, we know how to find the area. So the area is simply the integral from a to b of f of x dx. Okay. Now, the centroid is somewhere around here, and let's give it coordinates x bar, y bar. Think of this as the balance point. If you wanted to balance this, and this was a steel plate, where would you balance it so that if you laid it horizontal, it would be static, it would not move? Well, that's called the centroid. So what we need is the x-coordinate of the centroid and the y-coordinate of the centroid. So there are two formulas that you need to memorize. So the first one is the centroid for the x-coordinate is 1 over the area times the integral from a to b of x times f of x dx. It's like the area computation, except you put this little x over there. And for y bar, it's 1 over a times the integral from a to b of 1/2 parentheses f of x quantity squared dx. Alright, so copy down those formulas, and I would recommend that you memorize them. Our assumption is that it's the graph of a function, and it goes from the graph to the x-axis. Of course, in general, you can have objects anywhere, and there are similar methods you could use to compute their centroid. Much better to use calculus, a double integral, which you learn in calculus 3. But when you just have calculus 1 and 2 at hand, and you just know single variable integrals, then we usually restrict to this simple case. But in general, you can compute the center of mass of much more complicated things using double and triple integrals in 3 dimensions and things. Alright, so we have our formulas down. So why don't we try two basic examples. We'll do this one second, and we'll do a simple example here first. So we have to compute 3 things: the area, x bar, and then y bar. Alright, so let's try our favorite non-trivial example, the parabola. So y is equal to x squared on the range, on the integral, on the domain from 0 to 1. Alright, so our picture is something like this, and we're trying to find the center. That center would be x bar, coordinates y bar. Alright, so first we compute the area. The integral from 0 to 1, x squared dx Right now this should be easy. Right, x cubed over 3 from 0 to 1 is equal to 1/3. Alright, so the area is 1/3. So x bar is 1 over the area, so 1 over 1/3. The integral of x times the function, so x squared dx, from 0 to 1. So this is equal to 3. That's an x cubed, x to the 4 over 4. So x to the 4 over 4, evaluated from 0 to 1, comes out to be 3/4. Okay, so we found x bar so far, that's 3/4. And y bar, so 1 over 1/3, the integral from 0 to 1, 1/2 quantity function, so it's x squared, quantity squared, dx. Alright, so let's see. That becomes a 3 over 2. So 3 over 2. That's an x to the 4th dx from 0 to 1. So that goes to x to the 5th over 5. So it's 3/2 x to the 5th over 5. Evaluated from 0 to 1 again, is equal to 3/10. So 3/10. Okay, so centroid is located at the point 3/4, 3/10. So 3/4 is the x, 3/10 is the y. And notice that they are both between 0 and 1, and inside the graph. So it looks like it definitely could make sense. So this is where the center is. When you're here, you're in the center of the area. You can rotate around this point without trouble, without getting any wobbling and anything. That's the centroid. Alright, so let's do one last problem. We'll find the centroid of a triangle. So there is a little shortcut. We already know the area of a triangle. It's just 1/2 the base times the height. So 1/2 b times h is the area, and that saves us from having to do at least one integral. Alright, so let's compute x bar. So that would be the integral, 1 over the area. So 1 over 1/2 the base times the height, times the integral of x times f of x, negative h over b, x plus h, dx from 0 to b. Alright, so let's work it out. So let's simplify right over here. So let's see. So we get negative h over b x squared plus hx dx. So integrating that, we get negative h over b x cubed over 3 plus hx squared over 2. We can evaluate it from 0 to b. And don't forget, we do have to multiply by 1 over 1/2 b times h. So let's see what we get. So plugging in b we would get negative h. B cubed over b is b squared over 3. Put the b there, plus hb squared over 2. let's see. These are the same type of terms, so we can combine them nicely. A half minus a third is 1/6. So I still have to multiply out by this factor here. So let's see. So we get 2 over BH, right? Just flipping the 1/2 up. And this simplifies to 1 over 6 HB squared, which simplifies to 1/3 B. Okay, 1/3 B. So X bar is somewhere along this line, 1/3 B. 1/3 of the way. Now, without doing any work, you could probably guess that the answer here, the Y bar, also has to be 1/3 H. Because, well, we could have just called the base the height and the height the base. Could have flipped our rectangle, rotated our rectangle around. But let's work it out anyway, just to get some practice with the formula. Alright, so we found X bar is 1/3 B. 1/3 along this axis here. Alright, so let's go to Y bar. Alright, so Y bar is equal to 1 over the area times the integral from 0 to B of 1/2. So these 1/2 will actually cancel. So 1/2 parentheses negative HB, sorry, let me fix this, negative H over B x plus H dx quantity squared. Alright, so let's cancel out the 1/2s. And let's do a U substitution to really simplify this thing. So let's let U equal negative H over B x plus H. So when x is 0, U is equal to H. When x is B, U is equal to, when x is B, they cancel.